Intermediate Algebra Section 2.3. In this section, we're going to take a look at graphs that have straight lines, and they come from linear equations or linear functions. We have a definition for a linear equation called the slope-intercept form. Any equation of the form y equals mx plus b is said to be written in slope-intercept form and has a graph that is a straight line. This means this is a linear equation, and further, provided that y is by itself, the coefficient of the x term will be the value of the slope or the ratio describing the steepness of the line. The y-intercept, where this line crosses the y-axis, will have the coordinate 0, b. And let's put that into practice to graph some linear functions. In this first example, they're asking us to graph the following linear function. The f of x can be thought of as y. Function notation is just telling us some specific properties about this equation, but for our purposes, we want to graph this equation, so we'll replace the function notation with y. And next, we are going to compare it to the standard form of an equation, a linear equation, in slope-intercept form. Now, to graph this function or linear equation, we have two methods at this point. We could, one, pick some x values, solve for the corresponding y value, and then plot those points. Or we now can be a little more sophisticated in identifying components of the linear equation, comparing it to this slope-intercept form. Since y, or the function notation, is by itself, the coefficient of x will determine the slope of the line. There is no number in front of x, so it's understood that that is 1. So the slope of this linear equation, which by definition is equal to m, particularly has a value of 1. Now, slope, as I said, is a description of the steepness of a line, and it's also can be described as the ratio of the vertical change, we'll call that rise, over the horizontal change of this line, and we'll call that run. Any integer is understood to have a denominator of 1, so to help us with a ratio, we'll put our slope as 1 over 1. Well, we need to know more than just the slope. We need to know a starting place. And that second piece of information from the slope-intercept form is the intercept. More specifically, it is the y-intercept. The y-intercept, when an equation is in standard form, has the coordinates 0, b. We have a little bit of a problem when we compare our given equation to the standard form. It should be of the form plus b, and we have a subtraction. Using the definition of subtraction, we can change a subtraction into plus a negative. That now allows us to go ahead and determine that the value of b for this equation is a negative 3, which gives us the point 0, negative 3, the coordinates of the y-intercept. We now have the necessary components to graph this linear function. We will start with the point, and graphing 0, negative 3, you can see that the point is in fact right on the y-axis, thus the name, the y-intercept. And secondly, we'll generate the line by moving away with the slope. The description of the line steepness for this equation, which is the infinite set of points that satisfy this equation, is a rise of 1 for every run of 1. So from the y-intercept, I'll go up 1 and over 1 and plot a point. Repeating that, for every rise of 1, we run 1. We have a series of linear points, and if we connect those, we have a straight line with an infinite set of points. I have 3 noted here, but between these two is another, and between these two is another, and so on. Each one of these, if we could determine the coefficients, or if we could determine the components of the point, we would see that they satisfy the equation. Let's take a look at another example using the slope-intercept form to graph it. And here we're given a linear function. F of x is equal to negative 2x plus 3. And just like the last one, for simplicity's sake, we'll exchange the function notation for y, comparing it to the general form of slope-intercept form, where we have y by itself, so we can determine the slope by identifying the coefficient of the x term, and the coefficient of the x term in this case is a negative 2. And again, slope is a description of a vertical change called rise over a horizontal change run. And to have it as a ratio, we'll put the denominator of 1 without changing the value of the slope. The second piece of information we need to graph this is a point, and the specific point is the y-intercept, which has the following components: 0, b. In this example, the plus signs agree, so b has a value of 3. Our y-intercept is at 0, 3 this time, so out none horizontally, but up 3. This is where our line is crossing the y-axis. That's where we started first, and then we move on to the description of this line's pitch or steepness is telling us that they're rising a negative 2. Well, to rise negatively, it's telling us we're going to drop or move down. So from the y-intercept of 0, 3, I'll move down 2, and then it tells us to run 1, and that has a positive 1 on it, so down 2 and over 1. Repeating it again, a rise of a negative 2 and run 1. Now, just an option, if your graph has a negative slope and you run out of room dropping 2, negative 2 over 1, a negative divided by a positive is a negative, but we also would have the same if we had 2 over negative 1. A positive divided by a negative is a negative 2. So an alternative slope would be to rise a positive 2. So that means I'm going to go up 2 and then run negatively. And running negatively is to the left. So a rise of 2 and a run negatively. And if you notice, these points are all in a line. They are collinear. And if we connect them, we have the graph of this linear equation, which is the straight line, continuing infinitely in opposite directions, and a set of infinite points that are solutions to this equation. And anywhere we pick a point, if we use that slope of down 2 and over 1, we're right back on the line. Down 2 and over 1, we're back on the line. I might not have it quite straight here at the tail end. Using a straight edge definitely helps. Let's look at one more example of graphing a linear function using the slope-intercept form. Here we have our linear function. They're asking us to graph that. We will compare this to y equals mx plus b, the standard form for slope-intercept of a linear equation. Recognizing that the function notation can be replaced with a y. Since y is by itself, then, we can determine the slope. The slope is the coefficient of the x term, And in this example, it's a -1/2. And if you notice that negative is right even with the fraction bar, because we're going to be graphing that, it's telling us our slope is negative. We can either, from a practical standpoint, put an equivalent value of -1/2 or 1/2 as a description of our rise over run. The other component for graphing is a starting place, and the starting place will be a point, and our y-intercept is the coordinate 0b. Our signs agree, it's a +b, and we have a +2, so b is 2. Always start with the y-intercept and then move to the slope. Our y-intercept is at 0, 2. We have a slope of -1/2, which this is an equivalent. A negative divided by a positive is a -1/2, but this helps us with the graphing. A rise of a -1 means down 1 for every 2 that we run, or using this other option, a positive divided by a negative is a -1/2, and if we rise 1, we run to the left 2 with the negative there. And notice these points are all in a row. Connecting them, we have our straight line representation of the infinite number of solutions to this equation. One other point to make here, this example has a negative slope, and if you notice, eventually, and we can see it here, that if we number our quadrants, we can see that equations, at least this one, which is true of all, will eventually run between the second and the fourth quadrants if they have a negative slope. That last example had a negative slope, and if you notice, it's here between the second and the fourth quadrants versus the first linear function that we had. If you recall, the slope is positive, and look where this line is running between the first and the third quadrants, which is true of all linear equations. If you have a positive slope, it will eventually be running between the first and the third. And I say eventually if the graph is not extended and shown to draw into those quadrants. The fact that it's infinitely continuing in those directions, it will be in the first and third, and negative slopes always will run between the second and the fourth.